welcome back to three-phase circuits. We're on lecture 21 and we're going to cover chapters 12.4, 5 and 6. So all three of the other configurations. I don't know how long it's been since you watched the previous one where we did the Y-Y connection or the introduction to three-phase and then the Y-Y connection. We're going to start off now with what you can't see there, the balanced Y-Delta connection. All right, always balanced because that's what we're going to do. So let's just first look at what is a Y-Delta. So the first one, let me go to this, sorry. The first refers to the source and the second refers to the load. So is where you've got a balanced Y connected source feeding a balanced Delta connected source. Okay. I want you started so that we're going to see that better in the next section. Forget about this VP over there. Because in the first two sections, VP refers to V phase, and for the textbook, that's the same as a line to neutral voltage. In electrical engineering, V phase is always line to neutral voltage. I mentioned it in the previous lecture. But now we're going to get to where they make the V phase some of the line to line voltage, and then the wheels just come off. All right, so I don't want you to look at these. We're going to sort it out my way, the electrical engineering way. Okay, so this is what a Y-Delta looks like. You've got your line to neutral voltages on your source, line to neutral voltages on the source, line currents IA, IB, IC, and you've got your Z-Delta, Z-Delta, Z-Delta now, because it's Delta connected, and now IAB, IBC. IAB flows from A to B. BC flows from B to C and CA from C to A. All right, so that part makes sense. So we know which one is which one. Capital A connected to lowercase a. Uppercase B to B, uppercase C to C. Okay. What do we call those currents? Now the textbook calls these three currents, where do they do that, which I don't like. They call them phase currents. All right. Now, sorry, I made a note here in my textbook where they actually, oh, there it is, on the second page. Yeah, they talk about of the phase current. All right, IP. I do not like calling it a phase current because phase, when you hear phase, you must hear Y. So what are we going to call these currents? We're going to call them delta currents. All right, you've got a line current, you've got a delta current because it's the current that's flowing in the leg of the delta connection. All right, so I'm going to refer to them as the delta currents so that we don't get confused. All right, but how do we calculate IAB? So in the previous lecture, we saw how you convert from a line to line voltage, VAN, to a line to neutral voltage, to a line to line voltage, VA to VAB and vice versa. In this section, we're now going to introduce the second important equation and little phasor diagram that you need to solve chapter 12, and that is how to go from a line current to a delta current, how to go between a line current and a delta current. And we're going to do that through a KCL. And the textbook does it the same way. Let me just quickly go and check where that is. Here we go, in this section. All right, the line currents are obtained from the phase currents, delta currents, by applying KCL. Okay, so I'm going to redo this on the board in my way. Okay, so we are going to work in our delta circuit. So let's just quickly draw our delta load here. Now, so this section is going to go a little bit slower than the others, but we'll get to it. So IA is coming in here. So this is my A terminal. I think this was our B, and this is our C. So IAB is going in this direction, AB. And then going up in this direction is ICA. And we're going to do a KCL at node A. So where I'm going to write this. I'm going to need space. Yeah, let's do it here. So KCL at node A. Right. So all the currents that come in needs to equal all the currents that's going out. But I want the delta currents on one side and my line current on the other. So I'm going to write IA is coming in, IAB is going out. Now ICA is coming in, so I have to write it as minus ICA. Now I want an equation that relates IA with IAB, just like we had an equation that related VAN to VAB. So I want to substitute the ICA into something IAB. Now let's just quickly go back again to our little three-phase diagram. So that was A, B, and C. Now C now is represented by CA. How do I convert CA to AB, which is over there? Do I need to subtract or add 120 degrees? I need to go from this to this, CA to AB. So I need to subtract 120 degrees. So we can rewrite this as IAB minus IAB. I want it in terms of IAB. Sorry, it's the other way around. Angle 120 degrees. So to get from IAB back to ICA, I need to add 120. So what do I do with IAB? To get to the C bit, I need to add 120 degrees. All right. So now I can take the IAB out of this as a common factor, and you're left with 1 minus 1 angle 120 degrees. And if you punch that into your calculator, you will get IAB, IAB, and then 1 over root, I must get, root 3, angle, and now minus 30 degrees. Okay, let's rewrite this now a little bit. I want to write it now in terms of IAB then equals, so now I bring this over, it will be IA divided by root 3. The minus 30 degree must now come at the bottom, but I'm going to leave it at the top, so then it's going to become plus 30 degrees. Okay. So why do I want it written in this fashion? So our first little diagram and first equation that was important is we had this. So this was our VAN. And this is our VAB. And we said that VAB equals root 3 angle 30 degrees VAN. Now we want to write a similar equation. You see it's VAB equals something VAN. So that's why I rewrote the equation so that I've got IAB equals something IA. So now we've got the second one. If we were to write this in a little equivalent diagram. So that's the first one. Now, it looks a little bit different, hey? So what do I have to do with IA to get it to IAB? I have to make it smaller this time. Here it was multiplied with root 3. Now I divide by root 3, but it's still plus 30 degrees. Okay, so it looks almost the same. You would now have a triangle that looks like this way around. Maybe I should draw it a little bit bigger for you guys. It doesn't have to be this small. So now, what's the difference here? Now you've got the long one at the bottom. This is going to be which one? Is this now IA or IAB? This is going to be our IA. Still our reference. A stays our reference. And this is going to be IAB. So what do I have to do with IA to get it to IB? I have to take IA divided by root 3, make it smaller, and still add 30 degrees to it. So in other words, IAB equals 1 over root 3 angle 30 degrees IA. Right. That there is your, that's a 3. Alright, sorry. Root 3. These two pictures and equations, if you have those, you can solve any three-phase system. And that's what I want to show you with the rest of the problems that we're going to do, is how to use those two equations to solve any configuration of a three-phase system. It doesn't matter whether it's delta y, y delta, 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 y, y. We're always going to use these two equations to solve it. All right, a third little point here that I see that I made on my notes is the transformation. So remember what I said this in the previous lecture, is that when you've got a delta connected load or delta part in your circuit, we always want to convert that into the Y equivalent, so that you've got a Y-Y connection, not like now you've got a Y and a delta load on this side. We want to take this delta and convert it to a Y equivalent load. So to go from a, let's just write this again. I want to go from a delta to a Y equivalent. So what do I have to do with my Z delta to get to a ZY? Can you remember? Divide by 3 and then you get your equivalent ZY. Okay, sometimes you need to do that, or it's easier to do that. Sometimes you can get the answer straight without having to divide it by 3. I think the example that we're going to do now, you don't have to do that. Okay, I just quickly want to check if there isn't something that I left out in the textbook that I wanted to show you in this section. The Wye-Delta. Now they just have a, I see they just have figure 1215. They've got a diagram. Perhaps let me show you. So this little diagram over here. So it's pretty much what you have there, what we have there on the board now. Zoom in, move. There we go. So we've only drew that little section, the IAB and the IA there. Don't worry about where they're positioned. That the fact that our A is there. That the important bit is that you need to is that 30 degrees, the order in which they're in. Where they are sitting, snapshot in time. Okay. Then they've got that figure. They tell you that I line, all the magnitudes are the same. And see, IP for I phase. I delta. All right, I delta. Otherwise, we're going to get confused. All right, and then the per phase single phase equivalent circuit of a balanced Y delta circuit. See, now this is where they're going to get you confused, because now they talk about a single phase. So then you can't, IA is your line current that will now go through a third of that impedance. Single phase equivalent or per phase equivalent, always the Y equivalent circuit. All right. Let's work through. I want to go through practice problem 12.3. So let me quickly go and draw it on the board. Practice problem 12.3, they give us a three-phase system. So I've drawn the circuit. They obviously did not draw the circuit. No, of course not. And they give us VAB. Note capital VAB is 120 angle minus 20. So the fact that it's capital letters tells me it is across the load. They give me Z delta, 20 angle 40. So each of these three impedances is 20 angle 40 degrees. Is that now an inductive or a capacitive load? What's the angle, positive or negative? Positive. Okay, if it's a positive angle, it has to be an inductive load because it will give you a positive J. All right. So I've got the voltage between A and B. What do they want us to calculate? They want us to calculate the line currents, three of them, A, B, and C. IA is flowing there, IB, IC, and then also the delta current. So A to B, so this will be the one current is, where am I going to write that now? This is I AB, and if you've got IAB, you've got BC, and you've got VCA, because it's ICA, because it's just a 120-degree phase shift. Okay. Which one first? Which one is the easiest to do? And this is the part where you kind of have to forget that it's here's a three-phase circuit diagram. Just look at your circuit. I want the current through this impedance. If you want the current through an impedance, this IAB, which is the first of my delta currents, if I want the current through an impedance, what do I need? You need the voltage across that impedance. Do you have the voltage across that impedance? Yes, you do. It's PAB. That voltage is sitting across that impedance. VAB, the 120, is sitting across that impedance. So IAB is, VAB divided by Z delta. Now, I said we're going to solve three-phase circuits by using the per phase Y equivalent. All right. Yes, most of the times. But in this case, it would be a pretty big schlep to do it. The primary reason is I don't know the supply voltage. Yes, I can get it. I can get from VAB to VAN this voltage and then convert the Z delta into a ZY, then solve the Y equivalent circuit to get IA, and then when I have IA, I can get IAB. I can just get directly IAB right now, applying Ohm's law. That voltage is sitting across the impedance. Okay, so it's 120 minus 20 degrees across Z delta, which is 20 angle 40 degrees ohms. That gives you a 6 angle minus 60 degree amp. Right, 120 divided by the 20, and let me just check that I'm still fine. Yes, minus 60 degrees. Okay, knowing that, we can get then IBC. What do? Add or subtract 120 degrees. IRB angle to go from AB to BC. How do I know? Your little 3. So that's A, B, C. Or you can do A, B, B, C, C, A if you have to practice in the beginning. I want to go from IAB to a BC. I want to go from AB to a BC. Add or subtract 120 minus 120 degrees. So obviously after a few years or 2 decades or plus, you'll just remember that. So it's going to be 6 angle minus 180 degrees amps. All right. Yeah, let me not go there. All right, and then ICA, IAB angle plus 120 degrees. So that's going to be 6 angle 60 degrees amps. All right, so that solves for all your delta currents. What the textbook talks about, let me just check. They talk about, remember that textbook says phase currents, confusing delta currents. Okay, now I want to get my line currents, IA, IB, IC. Once you've got IAB, that second diagram that we've learned, long one, that's not 30 degrees, but you get the idea. Hey, short one, IAB, IA. That is how I convert between the line current and the delta current. So I think let's, for the sake of space, we'll fit it in here. So IA equals something IAB. What do I have to do with IAB to get to IA? I need to multiply it by root 3, okay, because it's the longer one, and I need to add or subtract? Subtract angle minus 30 degrees. All right. And then you will get 10.39, 10.39, angle, well, if it's to minus 90 degrees. Okay, for that one. All right. You could also have said that IA, if we used that KCL principle that we did earlier, and you could have said it's IAB minus ICA. So perhaps do that on your calculator and take this one minus that one, and you'll get to exactly the same answer. For IB, it's just IA angle minus 120 degrees. So that's going to give you the 10.39 angle. Ooh, guts. Minus 210. What's the wrong here? Mathematically nothing, but what's our boundary? It's plus or minus 180. So let's rewrite it as 10.39 angle 150 degrees, so that we just keep within our boundaries. And then for IC is IA, the 10.39. It's getting boring, eh? And then you add 120 to the 90 degrees, so it's going to be 30 degrees amps. All right, so we've just added the 120 degrees. So that's it for a Wye-Delta circuit. Let's quickly look at the Delta-Delta combination circuit. Very quickly, just the theory behind it, and then we're immediately going to jump into another equation. So here's our Delta-Delta circuit. So we've got line currents IA, IB. I've got my delta currents IAB. I've got line-to-line voltages, lowercase AB because it's on the supply side. Uppercase AB would be on the load side, like in this example on the board that we just did. Z deltas, okay, and again, all we want to go and calculate is different voltages. Okay, oh yeah, you see, all right. This is where the ostrich really hits the wind pump in the textbook's notation. Assuming a positive sequence, the phase voltages for a delta connected source are. No, the line voltages are the same as the phase voltages. I want you to take, I don't know what to do. If you could, I could have you rip out the page. A line voltage can't be a phase voltage. A phase voltage is a line to neutral voltage. So please ignore what they say. They don't get it confused. All right. Wherever you see a VP, just very, almost like VIP, just ignore it. All right. Very ignorable person. Just get rid of that. All right. I'm not going to go through any of those equations. We're immediately going to show you in practice problem 12.4 how to solve a positive sequence, balanced delta connected source, applies a balanced load, and now they give us the impedance for the loads and the line currents, and we're going to calculate the delta currents and the line-to-line voltages. Okay, let me just quickly draw the picture for this one. Right, practice problem 12.4. I'm a little bit ticked off at myself at this stage because this is the third time I'm going to do this now. The first time I thought I pressed pause, I pressed stop. So I had to redo it. Then I recorded it. And then when I wanted to do something again, I forgot to plug in my mic. Yeah, so I'm going to do this now for the third time. So I should be able to do this out of my head, I suppose. Anyway, here we go. Practice problem 12.4. Delta source, delta impedance, ZAB applies to all three of them. IA is your line current flowing through there. Now, they're not asking for IBC, ICA, or VBC, VCA. They're only asking for these two, because if you want the others, it's minus or plus 120 degrees. So what is now the quickest way to find IAB? So that's now that first little, or the second little triangle that we did for the currents. So you've got IAB there, and you have IA over there. So what do I need to do with IA to get IAB? Okay, capital, uppercase, lowercase, that obviously doesn't matter now. It's the principle that applies. Okay, what do I have to do with IA? I have to make it smaller, so I have to divide it by √3. And then I have to multiply it by 30 degrees, or add 30 degrees to my IA. Okay, so from the 960, I'm going to get 5.55, and the angle is a 65 degrees. All right, so I've just, the 9.609 divided by root, sorry, let's write that out. 9.609 divided by root 3, and then I have to take that angle, 35, I have to add another 30 degrees to it, and that gives me the 5.55 angle 65 degrees amps. Okay, so that's the quickest way to get to IAB. Then I want to find VAB. Where is VAB sitting? Well, that's your A. Sorry, I should have put that in there. That's B. That's the CA because it's connected to A. B because it's connected to C. C. B because it's connected to B, and C because it's connected to C. So IAB is that current that we calculated just now. And then VAB is what I want next, VAB. So I want the voltage across that impedance. Now, if you want the voltage across an impedance, you need the current flowing through the impedance. So I already have this IAB flowing through that impedance. So the quickest way is going to be VAB equals IAB times ZAB. So that is our 5.55 angle 65 degrees, and we multiply that by the 18 plus J12. Okay, and that gives us the 120. 120 angle. It wasn't such a nice angle, I remember. 98.69 degrees volts. Okay, so that's if you just do it the quickly Ohm's law method. I also want to show you how you would do this in the per phase equivalent, because the whole time I've been preaching, you take the delta stuff and you connect it to a Y equivalent. So let's find VAB using a Y equivalent circuit. All right. When we want to do a Y equivalent, we connect the delta stuff into Y. So here we need to connect the delta impedance into a Y equivalent impedance. So ZY is going to be my Z delta. We have to divide it by 3, and that then gives me 6 plus J4 ohms. So my new circuit is I still need IA. There's the line, that line coming in. Then I get to point A. I'm not going to draw the source now. We don't need that side. Perhaps, why don't we need that side? It is because what we want is VAB equals something VAN, but that we're only going to see now. Okay, then we get to VA, then we've got an impedance. What impedance is this now? This is now my ZY value. Okay. What is at this node? Remember, it's the per phase Y equivalent. So this isn't B or C. This is now your neutral point. So that means I've got plus minus VAN sitting over there, and I still have IA coming in. Okay, so we're going to go from VAN to VAB. How? Other triangle, VAN, VAB. So we're going to calculate VAN, Ohm's law again, and then from AN go to AB. So let's write it here. VAN is now equal to IA times ZY. IA is this 9.609 angle 35 degrees multiplied by, am I going to fit it in? No. 6 plus J4. Okay, so that gives me a 69.29 angle 68.69 degrees volts. All right, which means Now I can go and calculate VAB. VAB. What do I have to do with VAN? You have to take VAN, make it bigger, root 3. And you have to add 30 degrees to it, times VAN. And yeah, I don't have the space now, so you just take this, multiply it by root 3, and then obviously you need to get 120 angle 98.69 degrees volts. Okay, Bob's your uncle. Alright, so that is practice problem 12.4. The last little bit that we're going to do is 12.6 now, which is Delta-Wye connection. So let's just quickly run through that, look at the circuit for that one. There we go. Okay, I want to see my PDF as well. There we go. Alright, so I'm going to ignore, no, I want to do this bit of the theory I want to do, but a little bit different than what the textbook does. So what they want to do is, where's my circuit? I first want to look at the circuit. There we go. You've got delta connected source, Y connected load. And what we're going to do now is we're going to obtain an expression for IA as a function of VAB. An expression for IA, the line current, as a function of the line-to-line voltage. So the textbook does pretty much the same. No, do they? No, they don't. Okay. Oh, here it is. Here's the textbook equation that they get to, but I want to do it with you on the board so that you can see what happens. So I'm just quickly going to draw this circuit on the board, and then I'll get back to you. Okay, so this is not a practice problem. This is just a little bit theory, and I want to go through this just to illustrate that what they're effectively doing through this equation is to convert this into a per phase Y equivalent circuit to solve it. So our objective is find an expression for IA as a function of VAB. And what we're going to do is we're going to do a KVL in this loop. Now, the fact that it's now a three-phase circuit with a delta and a Y connected load, it's still just a circuit diagram. So all the laws, KCL, KVL, all of those still have to apply. So let's do a loop. We're going to start over here. So we're entering the minus of VAB. So minus VAB. Then we move along IA. What is flowing through the ZY? IA. And it causes a voltage drop plus minus. So it's plus IA times ZY. Move along in this loop. Okay, now we get to this one. Okay, but what voltage is this? What's flowing through this impedance? IB. IB is coming in from this side, so it causes a plus minus as IB comes in. So now we have to write minus because as we're coming in from this direction, we're entering that negative terminal, so it's minus IB ZY again, and that completes the loop, so this equals 0. Okay, but I wanted IA as a function of VAB, so I need to get rid of IB. Can I substitute IB with something IA? Yes, you can. IB is what? Let's write here, but IB equals something IA. What do you have to do with IA to get to IB? Now, I've been doing this for more than 20 years. If I don't draw the pictures, I get lost. Okay. B, C. What do I have to do with A to get to B? I have to subtract minus 120 degrees. Right, so substitute that in there and I get minus VAB plus IA ZY, because the IA is there, the ZY is there. I've substituted that in and I get 1 minus 1 angle minus 120 degrees equals 0. Now, remember, I want IA as a function of VAB. So let's take the IA ZY over here. Take the VAB across, and we divide by 1 minus 1 angle minus 120 degrees. If you do the number crunching on that, you're going to get a root 3 angle minus 30 degrees. okay, for that expression. Now obviously the ZY needs to go over as well, so in other words IA, and this is what the textbook then gives you, is VAB over root 3 angle, that's root 3 there, sorry, 3 minus 30 degrees, and now the ZY also gets to the bottom of things. Alright, you still need a voltage divided by an impedance to get a current. Now this is where the textbook stops, if I am not mistaken. Yeah, this is how the textbook then writes it. But I want to focus our attention on that part. What do you see? What am I doing with VAB here? Divide by root 3 minus 30 degrees. Let's go back to that first triangle, or that first vector diagram that we did. We had VAB, VAN. What do I get if I take VAB, I divide it by root 3, make it smaller, and I subtract 30 degrees? You end up with VAN. So what is this equation? This equation is nothing but VAN divided by ZY. So all they've effectively done here is to convert the delta source into its Y equivalent. Right. Previous example we did, I showed you how you connect this delta load into a Y equivalent load. Over here, they effectively, well, they stop there, but effectively what's standing there is VAN, which is just your line, your Y equivalent of the source. Okay, let's do a last example for this section. I'm just going to clear this. I'm going to keep the same circuit. I'm just going to add values to it. So the circuit stays, and this is now practice problem 12.5. What do they give us? They give us that VAB is 440 angle 15 degree volts, and they give us ZY. This impedance is 12 plus J15. 12 plus J, nice value. All right. What do they want us to do? They want us to find IA, IB, and IC. Exactly what we did now. Find the line currents. Okay. So what have we seen through that expression that I've derived now? What is it that we need to find IA, IB, IC? You need the line to neutral voltage. So we're effectively going to do this in a per phase equivalent. So from that derivation that we just saw now is we need VAN divided by ZY. Okay, how do I get ZAN? VAN. How do I get VAN again? Draw it again. You're going to draw that, well, you only need to draw it once because you're going to have it with you. I'm drawing it over and over again so that you can see how many times I use it. So I want VAN and I've got VAB. What do I have to do with VAB? I need to take VAB. I need to divide it by root 3 and I need to subtract 30 degrees. So minus 30 degrees. That gives me the VAN. So that is now, what is VAB? 440 angle 15 degrees divided by 15. Oh, no, man. My concentration is giving up. 30, and then from this 15 I need to subtract 30 degrees. Alright. So that gives me a value of, let me just quickly check here. Did I write that value down? No, this Mugu did not write it down. Let me just quickly calculate it. Okay, it gives me a value of 254. 0.03. Make it, it's fine. Angle minus 15 degrees. So then I plug this value in here. So the 254 angle minus 15 degrees. Divide by 12 plus J15. Okay, and that answer I've got ready. Plus 15, and that gives me 13.2 224 angle minus 66.34 degree amps. Okay, so that's IA. That's the current flowing through there. What will IB then be? What will IB then be? It's also going to be 13.224. But now, do you add or subtract? You subtract 120 degrees, which gives you, it's not going to, yeah, so let me write it down. So if you just simply subtract the 120, you're going to get minus 186.34 degrees. But now that's outside of our boundary, hey? So we need to rewrite it as 13.224 angle, and then it's going to become plus 1, let's just write it like this, 173.66 degrees amps. Okay, for IC, same magnitude, 13.224 angle. Now we need to take the minus 66 and add 120 degrees, and then you will get 53.66 degree amps. Okay. IA, IB, IC, quick. So if you've got the one, you've got the others. Now the tests and the exams, I mean, here I'll give you marks for magnitude and angle. I'm not going to give you marks again for magnitudes, unless it's wrong. I'll also subtract marks. Here I'm focusing on the angles. Okay. Yeah, so if the magnitudes are then, they have to be the same, but that part you should know. Okay, that's it for lecture 21. So we went through it rather quick. I wanted to go through it quick. The textbook makes way too much of it. And this is now the part why perhaps I should show you quickly what the textbook does. And there we go. So after you've done all 4 configurations, the textbook then hits you with this table. Let's zoom in. Let me just pull myself out of the way. Let's go there. Okay. So the textbook then gives you this table. A solution for every type of configuration connection. All the equations you must use for depending on what you want to solve. Now honestly, what's easier? Using this table or using my 2 equations? I've solved all our problems with just those 2 equations. So please go and put that on your notes. Go and practice your homework as well with those equations. You can't go wrong. Yeah, if you're welcome to try this. Good luck. You're gonna get lost. All right. So for the last lecture for chapter 12, not for the course yet, we will then look at 3-phase power. So if you don't get single-phase power yet, maybe you'll catch a few things when we do the 3-phase power. Okay, that's it from me today. After having to do a lot of things twice or 3 times because of my tiredness and stupidity. So I will see you again. You will see me again in the next lecture, and hopefully then I'm awake, and therefore I will not be doing the next lecture today. Maybe another day, not today. All right, see you next time. Bye-bye.